Okay, so we're going to do just a really quick review before we go on with our Lewis structures, just to remember, because some people haven't done Lewis structures before. So remember, the valence electrons are the electrons in the highest unoccupied or uncompleted energy level. The core is everything else. So the valence electrons are the ones in the highest level, the biggest energy levels, the biggest numbers. And we don't usually do transition metals or intertransition metals. So if we want to remember how we do this, so like, for example, beryllium, its electron configuration is 1s2, 2s2. So its outermost energy level is the 2. So it has 2 valence electrons. Or chlorine's abbreviated electron configuration. So 3 is the outermost energy level. So it has 7 valence electrons. Now, this is an ion, right? And so it loses these 2. So now we would say it has 0. And then bromine, as an anion, gains 1. So we would say it has 8 valence electrons. So we can find our valence electrons here, looking at our periodic table, or happens to be, again, like we talked last week, that they are the same number as the group numbers. So each of these groups has 1, 2, 3, 4, 5, 6, 7, 8. That is the number of valence electrons. Okay, so when we do this, you can see, I'm going to put these, we use dots to represent these electrons we talked about. So group 1 has 1 valence electron, so 1 dot. 1 dot is 1 electron. Group 2 has 2 dots, 2 valence electrons. Group 3 has 3 dots, 4 dots, 5 dots, 6 dots, 7 dots, 8 dots, right? And so these are how we represent the valence electrons. Now, covalent bonding is electron or atoms trying to fill their outermost shell. So for example, let's look at hydrogen. Now, this one isn't in your notes, but I just want to show you, for those of you who haven't done Lewis structures, why we even do Lewis structures. Like, what do they mean? Where did they come from? So hydrogen, right? It's a Brinkelhoff. It's the H in Hoff. It's 2 hydrogens bonded together. Now, why do these hydrogens bond together? So what they do is each hydrogen is in group 1, so has 1 valence electrons, but each hydrogen wants another electron, right? They both want another electron so they can have their outermost energy level filled. So what they do is they share. And so each of these atoms feels like its outer level is full. So this hydrogen thinks it owns these 2 electrons, and this hydrogen thinks it owns these 2 electrons. So they're sharing their electrons. So what we use is this valence electron dot structure, or a Lewis structure. And so we use dots to show our 2 valence electrons, and then we put them together, and now they're sharing the electrons. Now, how we show that they are shared is we draw a line. And this line represents 2 electrons. And this is a covalent bond. Both these hydrogens are sharing their electrons. And we call these Lewis dot structures. So this hydrogen believes it owns those electrons. And this hydrogen also believes it owns those electrons. But in fact, they're both sharing. Let's look at another one. Let's do HCl. So chlorine is in group 7, right? It has 7 valence electrons. Hydrogen is group 1, has 1 valence electron. So chlorine needs 1 more electron. Hydrogen needs 1 more electron. So if they both need 1 more electron, you probably figured out, what are they going to do? They are going to share. So each of these atoms feel like their outer shell is full. So chlorine thinks it has 8, and hydrogen feels that it also has 2, but in fact, they're actually sharing. So how do we do this with our Lewis structures, with our dots? So 1 dot around hydrogen, 7 dots around chlorine, again, because chlorine has 7 valence electrons, hydrogen has 1 valence electron. They're going to share here's these 2 electrons they're sharing, and how we show that they are sharing those electrons is we make those electrons into a line. And so this is the Lewis structure for hydrogen chloride. Okay, let's try oxygen. So oxygen in group 6, so it has 6 valence electrons. If we wanted to draw the orbital diagram, we could. Now, they're both too short, right? So what they do is they share 2 pairs of electrons. So now each of the atoms feel like their outer shell is full and they're sharing 2 pairs of electrons. So each oxygen now feels like it has 8 valence electrons. Remember, everyone wants 8. They all want to be like those noble gases. So how do we do that in our Lewis structures? So we have 6 valence electrons because there's six dots for 6 valence electrons. And then we put these together. And there's the 2 pairs they're sharing. And what we do is we create what's called a double bond. So that means they're sharing 2 pairs of electrons, so a total of 4 electrons. And we're going to talk about how to draw these in just a second. Okay, so let's try nitrogen. So nitrogen is in group 5, so it has 5 dots. So this time I should put 5 dots around there. I'm just going to rearrange this a little bit. In order for them to get 8, they have to share 3 pairs of an electron. This is a triple bond. Okay, so now we're going to go over how to draw these Lewis structures. So I wrote a few steps on the last video that was going in and out. So we're going to go through those again. So step 1, count the total number of valence electrons. So we're going to do NH3. Okay, so we're going to do NH3. So N, and then we have H, right? And I know you can't see this because of the color. Hold on. So I fixed this, now you can see it. Okay, so we're going to do NH3. So we have a nitrogen atom. There's only 1 of them. How many valence electrons does nitrogen have? It's in group 5, so there's 5. So there's a total of 5 electrons there. Hydrogen, there's 3 hydrogens. They each have 1 valence electron, so that's a total of 8 valence electrons. So again, this is the number we need to make sure of before and at the end of our Lewis structure. Okay, next step, draw the skeleton structure. So again, we want to draw this as neatly as possible. And again, any way that you have 3 hydrogens around your skeleton structure, that's correct. Now we need to count the number of electrons we've used. Remember, each line is 2, so that's 2, 4, 6 valence electrons. So we have used 6 valence electrons. So we started with 8, we used 6, which means we have 2 left. So if we have 2 valence electrons left, we add the rest as lone pairs. So here's our Lewis structure again. We have 2, 4, 6. Now remember, everyone wants 8. That's our octet rule. So we put our final 2 electrons on our nitrogen. So we have to check and see, check for octets. Remember, everyone wants 8 so they can be just like those noble gases. So nitrogen feels like it has 2, 4, 6, 8. So nitrogen has 8. Check for the octets, yes. Hydrogen, each hydrogen feels like it has 2, 2, 2. Hydrogen, remember, only wants 2 because it feels like it's full with 2 electrons. Okay, so let's go back to what we were doing, and I kind of expanded our rules here. So we just did NH3, and I can't erase these. So let's do, look at another one to do. Let's do, that one's too hard. Oh, let's do CCl4. That's a big one. Okay, and then we'll do one with another bond. So first thing, count the number of valence electrons. Carbon is 4, chlorine is 7, so 28 plus 4 is 32 valence electrons. And those of you who are awful at math, use a calculator, because the most annoying thing in the world is when you add it or multiply it wrong or subtract wrong, and then you get so frustrated and you're erasing so much, which, by the way, that brings me to the next point. Never use pen when you're doing a Lewis structure. I don't care how good you are at these, trust me. Never use pen when you're doing Lewis structure. Okay, so next step, draw the skeleton structure. So we have a carbon. Carbon always likes to go in the middle. We're going to put the Cl's around it. Check on that one. Next one, we have to subtract the electrons we use. So we've used 2, 4, 6, 8 electrons. So we need to subtract out 8 electrons. And again, those of you who are like, I mean, it's okay if you can't add or subtract. I'm a bad adder subtractor, so use your calculator. But the worst is when you, trust me, it's the worst when the mistake you made is adding and subtracting. Okay, so we have 24 left. So it says the next step is add the remaining as lone pairs. Now remember, everyone wants 8. So when we add electrons, we always add them as pairs. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so we've added all of our electrons. Now, it looks like we finished all of our atoms, so we don't have to make any double or triple bonds. We'll look at that one in a second. So now we need to check for octets. What does that mean? Again, does everyone have 8? So carbon believes it has 2, 4, 6, 8. So carbon's got 8. Happy carbon. Oops, I did not mean to erase carbon. Let's look at our chlorines. This chlorine has 2, 4, 6, 8, right? Because this chlorine believes it's all theirs. This chlorine has 8. This chlorine has 8, and this chlorine has 8. All right, we're good. Octets are checked. Okay, so let's try another one. Let's do CO2. Okay, carbon has 4. Again, just looking at the periodic table, 6 times 2. So that's a total of 16 valence electrons. So we draw our skeleton structure as symmetrically as we can. Again, that means just connecting it with a single line. Remember, each line is 2 electrons. Then we subtract, step 3 subtracts our electrons. So we've used 4, which gives us 12 valence electrons. Step 4, add the remaining as lone pairs. Okay, so we have 12 electrons, which means 6 pairs, right? Now, here's a little trick that makes your life easier. Always add from the outside in. Okay, so 2, 4, 6. Now I'm going to go the other outside. 8, 10, 12. Got it. Okay, I added my 12. Next step. Well, I'm going to check for my octets here, just to make sure, see if I'm good. So if we check for our octets, you can see this oxygen has 8, happy oxygen. This oxygen has 8, happy oxygen. But look at our carbon. Our carbon only has 4. Well, everyone needs 8, right? So we could just do this. But this would be incorrect. Why would this be incorrect? Remember, this is the number at the beginning and the end. You start here, you end here. Count your number of valence electrons. In the beginning, we have 16. In the end, we better only have 16. If I count my valence electrons here, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. No, I can't have 20. I can only have 16. So I can't add these. So let's check now. Again, we can only have 16. 2, 4, 6, 8, 10, 12, 14, 16. Okay, I've got 16 electrons. This is the most important step. You need to make sure, and you're going to be counting by 2 so much, it's going to be so annoying, but you are. You need to check. This is so important. At the beginning and end, do you still have 16? I would say 80% of the problems come from not the right number of valence electrons in the end. So check this. All right, so what do we do now? Here's where this step 5 comes in. Make double and triple bonds as needed. So what we're going to do is, so we've got 16 valence electrons. So we can't add anymore, we can't take away anymore, but we need to arrange these somehow so everyone has 8. So what we're going to do now is we're going to make a double and triple bond. So you take electrons from the outside and you put them in the middle. So I'm going to move this here and make a double bond. So I'm going to change that to red just so it's the same. So there's our double bond. Now we check again for our octets. This oxygen now has 8, check. This oxygen now has 8, check, right? Because it's oxygen, so I did 2, 4, 6, 8, because each line, again, is 2 electrons. But look at carbon. It only has 6, 2, 4, 6. Not a happy carbon. Okay, but again, do we have 16? Again, counting by 2 a lot. 2, 4, 6, 8, 10, 12, 14, 16. Yep. Again, we can't add, we can't subtract. All we can do is rearrange. So what are we going to do now? Put that double bond back there. We're going to do it again. So this, we're going to take from the outside. And again, doesn't really matter where you take it from the outside. And we're going to put it in the middle. Again, don't forget to erase it when you do that. Now let's check for our octets. This oxygen has 8. This oxygen has 8. And the carbon now has 8. Happy structure. But again, the last thing we do, check to make sure, is it 16? 2, 4, 6, 8, 10, 12, 14, 16. Happy structure, right? So we do this every single time. You get faster and faster at it, but I've probably drawn, I'm not even exaggerating, at least 1,000 Lewis structures, and I still go through these steps. So let's go through these steps for a couple more of these. And I can't erase this now, but it's on the other page. Okay, so let's try, well, we just did CO2. Let's try this one. SeOF2. So when it's written, by the way, with multiple atoms, it's saying this one is usually the one in the front, usually goes in the middle. So this one goes in the middle. Obviously, hydrogen doesn't go in the middle, so phosphorus goes in the middle. It's we've done electronegativity. It's the least electronegative atom that goes in the middle. So that's kind of how you know who goes in the middle, the least electronegative atom. So the one furthest away from fluorine, that's the one we want to put in the middle. Okay, so who's furthest away from fluorine here? Se is. So when we do this, first let's count our valence electrons. So Se, what group is Se in? Se is in group 6, so it has 6. Oxygen's in group 6. Fluorine is in group 7, and there's 2 of them. So we add all of these up, and we get 26 valence electrons. Okay, that's our step 1. Step 2, draw a skeleton structure. Again, we decided Se is the least electronegative, so it goes in the middle, and we put the rest of them around it. Like, how do we put it around it? As long as it goes around it. So how about, I don't know, I'm going to put an F there, and an F there, and I'm going to put an O there. It's around it. Okay, next step. Actually, I'm going to put the O down here, just so I have more room up there. Again, it doesn't matter as long as it goes around the Se. So now our next step is subtract the electrons used. So we've used 2, 4, 6 electrons. This gives us 20 electrons. Okay, that means we have to add 10 pairs. Outside in, 2, 4, 6, 8, 10, 12, 14, 16, 18, and look at Se. Se only has 6 here. So that's where the 20 will go. And then again, Now, we've used all of our electrons. We used 20, so we don't need to make double and triple bonds. A lot of times what people try to do is they try to automatically make double and triple bonds. Don't do that. Don't make them unless this part doesn't work. And I'll show you again when it doesn't work. Now we need to check for octets. Fluorine has 8. Se has 8. Oxygen has 8. Fluorine has 8. Our octets are good. Do we still have 26? You can't skip these last two steps. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Happy Lewis structure. You absolutely must check for octets, and you must make sure the valence electrons at the beginning are same as the valence electrons in the end. All right, let's do, so NO2 minus. So this one's it's got a little like extra piece on it. So nitrogen has 5 valence electrons, oxygen has 6, and there's 2 of them. This is an extra electron, so we add 1 electron. That is what this negative means. It means it's got an extra electron. So when you add this together, this gives us 18 valence electrons. Next step, draw our skeleton structure. So again, our least electronegative atom is going to be nitrogen, so it goes in the middle. The only way you can put 2 O's around it is that's the most symmetrical way, so we're just going to do that. Next step, subtract the number we've used. So we've used 4 electrons. This gives us 14. So again, we add these as lone pairs. So we subtracted the number of electrons used, add the remaining as lone pairs. Okay, 14 electrons. And again, outside in makes your life easier. 2, 4, 6, 8, 10, 12, 14. Right? I could only add 14. What I can't do, right? Now let me check, if I check my octets, 8, 8, 6. Oh, this one needs 2 more. Okay, all right, look, my structure's done. This is what I see all the time. People are like, look, it's done. Everybody's got 8. I'm good. This is good, great structure. No, not a good structure, because remember, the beginning and the end is the same step. Check. This has to be 18. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. No, not an okay Lewis structure. We can only have 18. So just because you see that you can add a lone pair doesn't mean you should. So here, this was these electrons I added, so let's get rid of them. Okay, so this structure here has 18 valence electrons. I cannot add any more. At this point, this is the point when we make double or triple bonds. Now remember, once we've hit this number, then we can't add or subtract. All we can do is rearrange. So we're going to rearrange our valence electrons. So we take an electron from wherever, and we make a double bond. So you take an electron from the outside, put it on the inside, zoop, and make a double bond. Okay, now let's check. Do we still have 18? 2, 4, 6, 8, 10, 12, 14, 16, 18. Ah, we have 18. Okay, now we have to also, again, check to make sure everyone has 8. This oxygen has 8. Check. This nitrogen has 8. Check, right? Because 2, 4, 6, 8. Because remember, they believe that they own both of those in the middle. This oxygen also has 8. So everyone has 8. We have 18 in the end. This is our Lewis structure. Now, we could have put a double bond on the other side. Absolutely. We absolutely could have done that. So we could have ended up with the double bond over here. That would have been perfectly fine. This is called a resonance structure, which we're going to talk about in just a minute. So we could have done that. Absolutely could have done that. Okay, so let's do another one. Let's do let's do this one. Just because that one's kind of a big one. So H3PO4. So P has to go in the middle, right? Now, these are this is H3PO4 and this is an acid, so the H's are always going to the end. So I'll probably give you the skeleton structure for this one just so you can see it. And let's just put in H there. And I'll just put an H here. So this would be the skeleton structure. And this one I'd have to give you that skeleton structure because it's kind of a lot. So let's do our valence electrons. I'm just going to do it like here. So that's hydrogen has 1 and there's 3 of them. Phosphorus has 5. Oxygen has 6 and there's 4. So add these up. Sorry, I know this is kind of a little crazy. This is 32. How many have we used? 1. Sorry, let me just do that in a different color. We've used 2, 4, 6, 8, 10, 12. So we used 12 valence electrons, which gives us 20 left. Again, pencil. So what we would not do, we never put lone pairs on hydrogen. No, because hydrogen, when it's connected to one thing, is already full. So we don't need to put lone pairs on hydrogen. So, and if we look here, our phosphorus already has 8. It's already full. We're good. So let's do, we have 20. So look at this oxygen. It only has 4. It needs 2 more. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This is a structure for phosphoric acid. Right, so here's our phosphoric acid structure. And again, we check. Don't forget to check. So we check. Does everyone have 8? 8, right? Hydrogen only wants 2. Happy hydrogen. Oxygen has 8. Oxygen has 8. Oxygen has 8. And then if we look at phosphorus here, try to do a different color. Phosphorus also has 8. So these are our Lewis structures. So I've walked you through how to do a few of these Lewis structures. Now we're going to look at how you can tell what Lewis structure is the best Lewis structure. And so because there are, as you can notice when you've probably been drawing these, there are multiple Lewis structures. So I'm just going to make this Lewis structure with the bonds the way we've been doing it so you can see this. Okay, so let's look at this Lewis structure here, which is SO2. So I've drawn the Lewis structure for SO2. So how we do the formal charges is you take the valence electrons minus the non-bonding electrons minus half the bonding electrons. Okay, so what does that mean? Oxygen. Oxygen has 6 valence electrons, right? So we're going to do this one first. So it has 6 valence electrons because we got that from the periodic table, right? Now, it has, if we look at our oxygen, it has 1, 2, 3, 4 electrons, non-bonding electrons, or four electrons, or 2 lone pairs. And then we take half of the bonding. And so you see how it's sharing, it's sharing here 2, 4, so half of that would be 2. I always do it like this. I always say when I do my Lewis, my formal charges. So oxygen has 6 minus 4 minus 1 bond, 2 bonds. So I just do 1 for each bond because technically it's half the bonding electrons. That gives us a formal charge of 0. All right, let's do sulfur. Sulfur has 6 valence electrons. It has 2 like free or lone pair non-bonding electrons. And then I just look here, I call it 1, 2, 3, minus 3. I mean, I guess it's 6 divided by 2, but I just count it each for one line is 1. So this gives us plus 1. So sulfur's formal charge is plus 1. Let's do oxygen. So again, oxygen has 6 valence electrons, and then it has 2, 4, 6 non-bonding electrons minus a bond. That gives us -1. Oxygen's formal charge is -1. Now, the sum of formal charges in any neutral molecule is 0. So do you see how if we have +1 and -1, the whole thing equals 0 because this is a neutral atom. If it's an ion, it equals the charge. And so we'll look at that. So we're going to do a couple formal charges here. So we just did sulfur. We just did SO2. So let's do this one here. Okay, so oxygen again. So we're going to do this oxygen here. It has, here's the formula. Right? So here's our formula. This is sulfur, we just did this one. So let's do our oxygen. Oops, I didn't mean to give you those answers. So let's do oxygen. Again, valence electrons minus lone pairs minus half a bonding. So this oxygen has 6 valence electrons minus 4 free electrons minus 1, 2. Minus 2, which gives us 0. So this formal charge is 0. Okay. By the way, hydrogen's formal charge is just always 0. Let's do this oxygen. 6 valence electrons minus 2, 4, 6 free ones minus 1 that's bonded. Right? So this one is -1. -1. Let's do this oxygen. 6 valence electrons minus 4 free ones minus 2 bonds. Right? So that is 0. This one is 0. Let's do nitrogen. So nitrogen has 5 valence electrons, and there's no lone pairs, so each bond. So we have 1, 2, 3, 4 bonds, plus 1. And again, you know that if your structure is correct, if the formal charge, when you add them all up, is 0, and we look here, +1 and -1, that makes a 0 formal charge. So this structure is indeed correct. Okay, so the best formal charge, or the best structure, is the one that has the least number of formal charges. So we're going to keep working on these formal charges, and we're going to do some crazy structures later. Okay, so let's look at these expanded octets. So now we talked about how electrons always want 8. Well, some of them can have more than 8, and some of them can have less than 8, and some of them can actually have odd electrons. So we're actually going to look at these now. So first of all, the expanded octets are ones that have empty d orbitals. And so we're going to look at these empty d orbitals in just a second. So first of all, here are these odd numbered electrons. So these odd number electrons, they're called free radicals, and they're super, super reactive. Have you ever heard of free radicals? Yeah, they're like bad for our bodies, bad for our skin. What they are, it's an unpaired electron. Now, usually an unpaired electron likes to hang on nitrogen, but technically you could put it on any atom. Okay, so those are these odd electrons. So I always say if you have a choice for an odd electron, use nitrogen. Now, how about those electrons that take less than 8? So they don't follow that octet rule. Well, one of those atoms is boron. So let's look here. So here's boron, and here I am giving it 8, right? So here's 8. You can see here's the formal charges like we just found out. So here's where I can draw these formal charges. So if we give boron 4 valence electrons, like in these structures, we end up with a negative charge on the boron and a positive charge on the fluorine. You see how this is a positive formal charge on the fluorine, or this one's a negative, here's another positive formal charge on fluorine. So another thing about formal charges, if you've got to have a formal charge, it wants to go on the most electronegative atom. So therefore, fluorine never, ever, ever wants a positive formal charge because fluorine is our most electronegative atom. So these are all very unhappy I mean, we could make them do it, but they don't want to because they're very unhappy. So if you've got a formal charge and a negative formal charge, the negative formal charge always wants to be on the least electronegative atom. So let's draw boron without 8. So here is boron with only 6 valence electrons around the middle atom. And so boron is one of these structures. So can you do this? Yeah, but does boron want to do it? No. This is what boron wants. Because if we look at the formal charges here, right? So boron is in group 3. It has 1, 2, 3 bonds, which gives us a 0 formal charge. We look at fluorine, right? Fluorine, and each of these fluorines is going to be identical because they have the same bonding around them. So fluorine has 7 valence electrons. 2, 4, 6 minus 6 free electrons minus 1 bonding. That gives us 0. So this structure has a beautiful Lewis structure with no formal charges at all. So this is going to be the favorite structure. The favorite structure is the structure with the least total number of formal charges. If we can get all zeros, that's going to be the structure we use. And so boron doesn't do 8. It only does 6 around the central atom. So boron only does 6. So the lesson is, if filling the octet of the central atom results in a negative charge on the central atom and a positive charge on a more electronegative outer atom, don't fill the octet. Okay, so who does this? Boron does this, and aluminum does this. And then we'll talk about beryllium later. But these two are notorious. They only want 6. Because of this rule. So they are notorious. Boron and aluminum, just put those in your brain. They only want 6. Okay, what about those that can take more than 8? Okay, so look at this. This is the structure, and this we'll see with formal charge is a happy structure. But look at phosphorus right here. Look at how many valence electrons it has. It has 2, 4, 6, 8, 10. What? How can it do that? Well, the key is in the electron configuration for phosphorus. Okay, so I'm just going to draw the whole electron configuration. So phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. This is the valence electron, the electron configuration for phosphorus. But it only has 3 electrons in the p. But there's a 3d orbital, right? Because the third energy level, so remember, the only difference between the 3s, the 3b, and the 3d is the shape. They're the same size and the same distance away from the nucleus. So technically, this 3d orbital is there, it's just empty. So what we can do with these electrons that can do what we call expanded octets is they'll put electrons in their empty 3 or their empty d orbital. So who can do this? Anybody 3p and below. So phosphorus, sulfur, chlorine, all those and below can do this. So 3p and below, because they've got an empty 3d orbital, right? Because remember, this is a sphere, right? This one looks like a dumbbell, and this one looks like a clover leaf. But they're all the exact same size. They're the same distance from the nucleus. So the electrons can jump from one to the other without a problem. Okay, so now, and if we look at these formal charges, look at our phosphorus. Phosphorus is in group 5. And this is 1, 2, 3, 4, 5. 5 minus 5, that's a 0. Happy phosphorus, because it's a 0. All these fluorines, you see they're all identical here? Fluorine, so let's just do this one. 7 valence electrons, because it's group 7. 2, 4, 6 free electrons. 1 bonding. 0. All these fluorines are also 0. Happy Lewis structure, right? Least number of formal charges, happiest Lewis structure we've got. Okay, so we're going to practice some of these formal charges. Let's do let's do this one. So I'm going to do a couple of these and then I'll just show you the answers so you can practice these later. So if we go from nitrogen, again, nitrogen, I'm going to do this one right here. This is the one I'm doing. It has 5 valence electrons minus 2 lone pairs minus 1, 2, 3 bonded electrons. So 5 minus 2 minus 3, that's 0. Okay, let's do this oxygen now. 6 valence electrons minus 2, 4 free electrons minus 1, 2 bonds. Again, 0. Let's try this oxygen. 6 valence electrons minus 2, 4, 6 free electrons minus 1 bonding electron. That's a negative 1. So this one is negative 1. So remember how we talked about how the formal charge is 0 on a neutral atom? Well, this is an ion, and its charge is negative 1. Right? So its charge is negative 1 here. So the formal charges add to the same as the ion. So the formal charge for this whole molecule, it's got that negative 1 there, which reflects that negative 1. Right? So same thing goes for, let's try this one. So this one, the formal charges need to add to negative 2 because the charge on the ion is negative 2. Let's try. Okay. Well, all of these oxygens, you see, have the same bonding, so they're all going to be the same. Because they're all 6 lone pairs with 1 bond. So at least it's less we have to do because they're all the same. Which, by the way, you're going to recognize these formal charges. This is the same thing right here, where this one was negative 1. 3 lone pairs and a bond. It's going to end up with a negative 1 formal charge, but let's try. Let's do this oxygen. 6 valence electrons minus 2, 4, 6 free electrons minus 1 bonding equals negative 1. So this is a negative 1, this is a negative 1, and this is the negative 1, because they're all the same. All right, let's do sulfur in the middle. So sulfur is in group 6, minus 2 free electrons, minus 1, 2, 3 bonding electrons, which gives us a plus 1. Okay, remember they need to add a negative 2. Well, negative 1 plus negative 1 plus negative 1 is negative 3, plus 1 is indeed negative 2. So those are our formal charges. And the rest of those we can do at a later time. But formal charges is pretty fast once you get them. A little weird at the beginning, but they're not so bad. Okay, so now we're going to talk about resonance. And we actually already sort of previewed what a resonance structure is. A resonance structure just means that there's more than one way to draw a correct Lewis structure. So remember when I drew this Lewis structure and I put the double bond over here? Right? That would be resonance. More than one way to draw a Lewis structure. Okay, so we're going to look at this. So Lewis theory talks about how electrons between atoms are bonding. And an extension of this is resonance, which means that the bonding is delocalized, which means that the double and triple bonds can move around and it helps stabilize the molecule. So resonance really is just more than one way to draw a Lewis structure. Okay, and again, the only difference can be the electrons. You can't change the atoms around, just the electrons we're changing around. And so when you have a resonance, it means that there's more than one correct Lewis structure, which means that only drawing one Lewis structure is actually incorrect. So for example, I'm just going to draw this the way that we have been, which not letting me change my colors. Hold on. Well, that didn't work. Okay, well, we're just going to do it like this because it's kind of weird with these lone pairs. So actually just ignore those. So do you see how the double bond is on this side and is on that side? So just drawing one of these would be incorrect. So we have to draw both of these. And so what you're doing is you're looking for multiple bonds in lone pairs. That's what you're looking for in resonance. So we'll look at this more now. So the rules of resonance. They have to have the same connectivity, which means you can't move the atoms around. All you can do is move the bonds and the electron, the lone pairs around. All the rules apply. You still have to have the same number of valence electrons that you did in the beginning and the end. The second row elements, like period 2, energy level 2, can only have 8. You can't expand them until you get to period 3. And then the formal charges have to be the same. So if it's 0, they're all 0. If it's -1, they're all -1. Okay, so let's look at this. So here's our first structure. So again, we just did these formal charges. These are both -1. We just did both of these like 3 times. Let's look at this one again. So this one's going to be 6 minus 4 minus 2, right, which is 0. Nitrogen here is 5 minus 1, 2, 3, 4. So nitrogen is going to be plus 1. So those are our formal charges. Now, so what we do, so here's a way to draw formal charges. You can do it, I call it artistically, or you can do it systematically. Whichever one works best for you is fine. I'm going to do it systematically because I'm going to give you these steps. So you move the electron pairs from the atoms with a negative formal charge towards the atom with a more positive formal charge. So what does that mean? So here's a negative formal charge, here's a positive formal charge. So we're going to move them from here to there. Okay? Now when we do that, we can still only have 8. So this one has to move out there. And then our new structure looks like this. So basically you can see we just moved our double bond just like I showed you before. Now I'm going to look at this one for a second. If it's a third row or below, then you can keep bringing the electrons pair until that formal charge gets to 0, even if you expand the octet. So nitrogen's in group 2, so we can't expand the octet. So by the way, there's another structure we can draw here. So here's the double bond here, here's the double bond here. We could have also moved the double bond here. Now again, our Lewis structure has to be the same. Our formal charges end up adding to the same, but if we look here, this is a +1, right? -1, -1. So we actually have 3 separate structures. Which structure is correct? A blend of all of them. So when you have a resonance, you gotta draw all the resonance structures because one structure doesn't give the complete story. It's like when you look at a seashell. If you only look at one side of the seashell, you're not getting the complete story. You gotta look at both sides. That's like resonance. If it's got resonance, you gotta draw all 3. Okay, so first draw the Lewis structure that minimizes the octets like we did with our steps during our octet rule. Then we assign our formal charges. Then we take electron pairs with negative formal charge, move them towards the positive. If it's a group 2, you remember can't expand the octet, but if it's a group 3, you can. Okay, so here's a Lewis structure. So these formal charges. So we know that this is a -1 and -1 because we've done this one a bunch. Let's look at these two because remember these two are bonded the same, so they have the same formal charge. 6 minus 4 to 4 minus 2. So these both are zeros. Let's look at sulfur here. Sulfur is 6 minus 1, 2, 3, 4. So it's a +2. Okay. So take it from the negative formal charge towards the positive formal charge. You just erase this so it's not like you're seeing both of these. Okay, so I'm going to take it from a negative formal charge to a positive formal charge. I'm going to do with this one too. So when I do that, can't change my colors anymore. So I won't be able to erase. And we do the same thing with this. Here ends up being our new resonance structure. Usually I do it in one step and I erase it, but it's not letting me erase right now. So if we look here, now this is 0, and this is 0. But do you see how the formal charges still add to the same? So -1 plus -1 is +2. So the total is 0. These are all zeros, the total is 0. So this is a Lewis structure based on octets. This is a Lewis structure based on formal charge. So either of these is correct. It kind of depends on which one they're asking for. So when you do your Chem 101, it'll say based on octets, what's the Lewis structure? It'll say based on formal charge, what's the Lewis structure? So usually it's this, and this is the special one in your Chem 101 that you're going to see in just a couple minutes. Okay, so again, how do you know which resonance structure to use? The fewer formal charges, so the fewer pluses and minuses there are, the better. The smaller the formal charges are, the better. And the negative formal charge, if you've got to have a negative formal charge, we put it on the most electronegative atom, right? So less formal charges, smaller formal charges. If you got to have a negative, make sure it's on an electronegative atom. So this is how you can tell what is the best structure. So let's look at these structures that we just did before. So this is the same example we've been using since the beginning. Question is, are there better structures? Well, this one is 0, 0, 0. I put all the formal charges on here, by the way. So no, this is it. This is it. There it is. Okay, let's see this one. Okay, let's look at this one here. So SE is +1, and this is -1. So we take the lone pairs and we move them in. So once we do this, this becomes a double bond. And aha, look, it's letting me change it with my mouse. We move that here. This is our other structure. And when we do that, let's look at our new formal charges. Oxygen, here 6 minus 4 minus 2, 0. Se is 6, group 6, minus 2, minus 1, 2, 3, 4, 0. Ah, look, we just got a better structure. We just moved it in. And it's okay that we expand this octet. Like, we look at our Se right now, it's got 2, 4, 6, 8, 10 valence electrons around the central atom. That's okay because Se is below group 3, or below the third period, so it can expand its octet. This one we've already drawn. We just drew it the other way. Let's look at this here. Oh, here's one. Look at whenever you see a formal charge on the middle atom, that's like a whoa, ho, ho, there's another structure that can be drawn. And so we're going to take here, this one's negative, so we take these and we make a double bond. That ends up being, make it so you can't see these. So I made a double bond. So now oxygen has a formal charge of 0, and phosphorus is in group 5, 1, 2, 3, 4, 5. It also has a formal charge of 0. Found a better structure. All right. Again, whenever you see a negative formal charge on the outside and a positive on your inside, that means, haha, we could expand octets. All right, this one. So all of these oxygens have formal charges, so we could choose any of them. So we could move this one in the middle, or we could move this one in the middle, or we could move this one in the middle, right? It's going to give us a lot of opportunities here on this. And so you can see here, I just have all three. Here's the one we had. Here's the one moving one of them in the middle, moving another in the middle, and moving another. So this structure here has 4 different resonance structures. Here's the one that we just drew, and here's the one we just drew. We did this one earlier. This one, if everybody has 0, there's nowhere to go, right? If everybody already has 0, there's no resonance if everyone has 0 on their formal charges. Okay. Drawing resonance takes a lot of practice. Your quiz next week is on Thursday, and so you have really until Thursday to get good at resonance. In Chem 101, you're going to practice it, but your next quiz will have resonance on it. So we have a week or so to work on that. Okay, now trends in bond length. So the difference between single, double, and triple bond. So the greater the bond, single, double, or triple, the shorter the bond is, and we're going to talk about that. So in general, so you can see here's a triple bond is shorter than a double bond is shorter than a single bond. And that holds true for same atom or different atoms. When comparing like atoms. So bond length generally decreases from left to right. So you can see carbon is longer than the carbon nitrogen, which is longer than the carbon oxygen. And again, this is because of the attraction, the electronegativity, right? We talked about this one. These guys are nonpolar because they're perfectly nonpolar covalent. These are not pulling equally. These are pulling even less equally. Remember, this one's a little bit negative and this one's a little bit positive. This one's a little negative, this one's a little positive. But this oxygen is more electronegative. So it's saying, come on, come on, carbon, give me your electrons, give me your electrons. And it's pulling carbon closer. So the bonds are actually shorter. So the more polar it is, or the greater the difference in electronegativity, the shorter the bonds are. So, and bond length increases as we go down, well, because the atoms are bigger, right? So like here's like an FF, and then like here's ClCl, well, here's like FF, and then ClCl. I mean, they're further away from each other because they're bigger atoms, right? I didn't draw that very well, but they're bigger atoms. So in general, as the bonds get longer, they also get weaker. Okay, so we've talked about ionic bonds, and we've talked about covalent or molecular bonds. Ionic bonds between a metal and a nonmetal, transfer of electrons. Covalent bonds or molecular bonds are sharing electrons. Those are 2 nonmetals. Now we're going to look very quickly at metallic bonds. So metallic bonds are between metals. So the low ionization energy of the metals allows them to lose electrons very easily. So if you think about it, if you have 2 metals, they don't really want to gain any electrons, and they also don't want to share because metals want to lose electrons. And so I think of it as a game of hot potato. The metals are like, no, I don't want every metal's like, I don't want my valence electron, you take it. And the other metal's like, no, I don't want it, you take it. And so what you end up with what we call a sea of electrons. Because all of these metals are like, I don't want my valence electrons, and so they're releasing their valence electrons, but at the same time, those valence electrons are attracted to the cations. So it's kind of like these electrons are free to move. And so it's kind of an interesting thing. So once they let go of the electrons, then they become cations. So then they're like, oh, but I want the electron. But then when they get the electron, like, no, I don't want the electron. So it allows for this freedom of movement of these electrons. So the electrons are kind of like floating around in a sea of electrons. And we literally call this is what metallic bonding is, a sea of electrons, where the electrons are free to move throughout the metal. And that's why metals can conduct electricity, because the electricity is just the movement of electrons. And so if metals have moving electrons, that's why they're so good at conducting electricity. Think of like power lines. How do we move electricity? Power lines. What are power lines made of? Metal, right? And so that's how metallic bonds are done. Okay, so now I'm going to share, hold on one second, you guys can see this. I want you to see my Chem 101. Okay, So here's Chem 101. I want to show you how the bonding works in Chem 101 because it's a little bit different. Okay, so we're going to do some Lewis structures here so I can show you how you're going to do your Lewis structures in Chem 101. Let's do an easy one first. Let's do HF. Okay, so when you do this, so we want to draw the Lewis structure for HF. And unfortunately, I'm not sure, I can't write at the same time I do this, so I'm going to have to talk through it. Okay, so how you change the element. So the element that's red is the one it's talking about. So you go down here to change the element, and we want HF. So I want H. I want to change this one to F. Okay, now when I do this, first thing I gotta do is I need to count my valence electrons. And so you don't have to put these valence electrons on here if you don't want to, but like so hydrogen has 2 and right now fluorine has 2. Well, I know that fluorine needs to have 8 valence electrons. So hold on 1 second. I think I can write on this now. Okay, so if we do our valence electrons, if we have H and F, hydrogen has 1 valence electron, fluorine has 7, which is a total of 8 valence electrons. So I always do these structures on paper, and then I do them on Chem 101. But as you get better at this, you're going to be able to start seeing these Lewis structures. So here's my skeleton structure right here. So I've used 2, which means I have 6 left. Where am I going to put those? I'm not going to put it around hydrogen. I'm going to put them around fluorine. So what we do is you go over here to, I have to, unfortunately, I can only have it on one at a time. I wanted 6 electrons on fluorine. Right, so now if I check for my octets, you can do this, watch our valence electrons. It checks them for you, right? This fluorine has 8 and this hydrogen has 2. Our octets are correct. Do we still have the correct number of valence electrons? Yep, we do. If we look, we've got 2, 4, 6, 8 valence electrons, the same number of valence electrons we want in the beginning. And then you just click done, and they're like, okay, is this what you want? Yep, that's what I want. Correct. So let's do another one. Let's do water. Okay, so I'm drawing it for water. So you see how there's only 2 atoms here? So what you can do is you can just see over here it says the number of bonds. You can just change it to 3. So if I needed 4, I would just do this. You can just do this at the very beginning. Or you can do it at the end, or in the middle. I'm just going to do it in the beginning. So again, we want to put the least electronegative element in the middle, which is oxygen. And again, you can look at which the least electromagnetic element is because here's a periodic table for you. So I'm going to put hydrogen on one side, click here, hydrogen goes on that. That is my skeleton structure. So I have water, which is 6, and then 1, hydrogen is 1 times 2. We said it was supposed to be equals, which equals 8 valence electrons. So I've used 2, 4, which means I have 4 left. Now, where am I going to put those? I'm going to put them around oxygen, not around hydrogen, because remember, hydrogen is full at 2. So I'm going to go here, click on this, go over here to electrons. I want to put 2 pairs of electrons on oxygen. And you're going to see it actually puts it in the correct geometry, which we're going to learn about on our next class. And so here we are, and we check. Look, watch, we can do this. Oxygen has 8, hydrogen has 2, hydrogen has 2. It's kind of nice. Checks your valence electrons for you. It'll also put in your formal charges. It's kind of cool. And this is 0, 0, 0. And then we just click, done, show answer, correct. So you have a lot of Lewis structures that you're going to be doing for this section. So let's look, here's SEOF2, we actually did this one in lecture. And you see how this one says, follow the octet rule. So that means follow the octet rule. And then if you get down here, minimize formal charges. So then you use the formal charge rule. So it'll tell you which one to do. And so when you're doing, let's just do like, let's do HCN. Oh, no, this is not a multiple choice question. I mean, not a free response. Let's do, yeah, this is when you have to, nope, not when you have to draw. Sorry, you don't have to draw all these. Sometimes I'm just going to ask you how to do like the different questions on them. So I think this one is draw and, oh yeah, this one is draw and formal charges. So this one wants us to draw these and do the formal charges. So when we draw this, CO, carbon, click on the element, change the element, O. So again, carbon, I draw this, carbon has 4, oxygen has 6, which equals a total of 10 valence electrons. I've used 2, which means now I have 8. So I'm going to first use 8 valence electrons. So if I do this, I'm going to use 8 valence electrons, right? So there's 2, 4, 6, and I'm going to put 2 on carbon. Okay, but when I do that, look at my octet. Look at, that's when we check for our octets, right? This has 8. This only has 4. Okay. So in this case, what we need to do is just remember, this has 4. Oops. Zoom out. There we are. So this one has 4 and this one has 6, which is a total of 10. So we have 2, 4, 6, 8, 10 right now. So I can't do this. I can't do that because that's more than 10. All I can do is have 10. So what I've got to do now is rearrange. So I need to make double bonds. So how you make double bonds in Chem 101 is you click on the bond, and then you see over here it has a number of bonds. So I'm try 2 bonds. Oh wait, that's bond, sorry. Type is over here. Bond type is over here. This is a single bond. So if I try a double bond, check for my octets here. This has 6, this has 8. It's still not okay. Not enough. I can't add, I can only rearrange. So if I try another bond, now if I check for my octets, well, action can do this, valence electrons. Oops, let me just do it. This one has 12. Ooh, something's not going right here. I've got 12, but I've got a triple bond. So what I need to do is come over here and go, oh, this is, I can only have, this is not right. So I need to change my electrons here. Now I'm going to check for my, remember I need to have 10 valence electrons. 2, 4, 6, 8, 10 valence electrons, octet 8, all set. Now, let's say that when you're doing this, you're like, oh, I don't like what I just did. You can just go back. And if you're like, oh, this is really wrong, you can just reset and begin to the beginning, right? And then you can do your formal charges. You can turn those on or off. So this is how we do Lewis structures in Chem 101. They take a little bit to get used to at the beginning, but it gets easier as you go. Okay, so we're going to stop there. This is, so we've done Lewis structures, and we did a little bit of metallic bonding. We did formal charge and resonance. So now all you have to do is practice, practice, practice. The, sorry, when I go back here, I need to go back. This homework is long. It's about 3 hours because Lewis structures, when you get used to it, it's quicker, but it is a bit long. So this also has lattice energy in it also. And this is due on Saturday. So make sure you start working on this ASAP with these Lewis structures. And then we will continue on, which is with molecular geometry, which is using Lewis structures. So make sure you're cool with your Lewis structures by our next lecture. All right, that's all we have for today.